Quite get to the very last thing I wanted to do, and that was to show you some simple results of the resolution equation and show you the impact of those three factors, the N, the plate count, the retention factor, and the selectivity. So remember, that's what we're calling the general resolution equation, or the Purnell equation. And I've got it built into this spreadsheet with sliders. For the plate count, you can only go from 5,000 to 25,000. For the first retention, for the retention factor of the first peak of a pair of peaks, you're only allowed to change it from 0 to 10. That's there. And then the selectivity factor, which is this lowest, the last slider, we're only going to let it vary from 1 to 1.2. It's a very narrow range compared to the other variables. Okay, we're going to see what happens as we change the parameters. First, we'll vary the plate count. Oh, by the way, the purple peak, the little purple peak, that's a peak that I put at the dead volume of the column, the dead time of the column. So for instance, in GC, you put a little methane or propane in your sample, and that'll show up pretty much unretained. You know, at a column temperature of 50 degrees centigrade, they're just not retained, they're gases. Or it could be an air peak in GC. In LC, we usually have to add something to the sample to see the dead time, see the dead volume. And a compound like uracil, which is really, really, really water soluble, and it has no charge on it, would be essentially unretained. So we just want to know where the dead time of the column is when we look at a chromatogram. It's really important to know where the dead time is. So the first little peak is a dead time marker peak, and then the second peak, well, it's the second peak. And we'll see if it's one or two peaks. So I'm going to increase the plate count. And I just increased the plate count from 5,000 to 11,800. That's a big increase in plate count. I'm not changing the column length. I'm waving a magic wand over the column, and the plate count's increasing. And then if we run it all the way up to the limit, 25,000, that's all you can get. That's the best you can do. Now I have no way, there's no way I can tell you how to increase the plate count a factor of 5 without some major changes, like making the column 5 times longer. If you made the column 5 times longer, it would take 5 times longer for the stuff to come out of the column, and I didn't change the time scale, so there was some serious magic there. But let's run this back down to its initial value. Okay? Now, let's change the selectivity. And right now the selectivity is 1.098. Let's call it 1.1. And let's increase it, 1.108. .12, beginning to look like there might be something else in there. Well, surely there's something else in there. Definitely. And that's the best we can do. Okay? Let me put it back to roughly where it was before. That's about where it was before, okay? Now, looking at the time scale here, would you say that this peak is well retained? It's not, because it's pretty darn close to the dead marker. In fact, the dead marker comes out at 10 seconds, and this peak is coming out at about maybe 14 seconds, 13 seconds, something like that. So 13 minus 10 divided by 10. So the retention factor is a lot less than 1. Oh, sorry, wrong variable. Let me put this back to where it was. That's perfect. Okay, K prime in fact is 0.3 if I look in the green box. Bam. I increased the K prime of the first peak to 3. Now it's 5. Now it's 10. The problem with this initial separation is that there's too little retention to start with. And if there's too little retention, you really need a huge increase in plate count, or you need a relatively larger increase in selectivity to do the job. But and adjusting N and adjusting alpha is a lot harder in general than adjusting retention. In gas chromatography, if you ever want to get more retention, all you have to do is lower the column temperature. That's it. That's not hard to do. In liquid chromatography, depends on what kind of liquid chromatography, but what you do is you make the eluent, the mobile phase, a weaker eluent, and you can increase the retention. Now, for instance, in reverse phase chromatography, you would add more water to the eluent. In ion exchange chromatography, you would lower the ionic strength of the eluent, or you would diddle with the pH of the eluent, depending upon the chemistry of the phase and the chemistry of the ions involved. In normal phase chromatography, you would use a weaker, a less polar eluent than your initial eluent, and you could immediately increase retention. The absolute retention is one of the easiest things to change in chromatography. So, again, the first law of chromatography is if you don't have retention, you can't get resolution. This is already in your Google Drive, and you can download it and play with it to your heart's content. Okay. Good. So now, let's get on to the next material. And the next issue to take up is what's called the general elution problem. And I'll describe that in a minute. And then we're going to get into some somewhat deeper theoretical issues. Not that they have no practical significance, they do have practical significance, but they're somewhat more advanced topics. And the first of these is a concept that's called the effective plate number. And I'll define it and explain why it was invented. Then we'll talk about a very important concept called the peak capacity. The peak capacity is defined as how many equally well-separated peaks can you fit in between 2 points on a retention scale. So between volume 1 and volume 2, or between time 1 and time 2, What's the maximum number of peaks that are equally well separated that you can fit in that space? Sort of the flip side of peak capacity, because in peak capacity, we assume that the peaks are equally well resolved. And so the elution sequence, the band spacing, is highly controlled. There's an alternative approach which is more realistic, called statistical overlap theory. And this was developed in the mid-1980s by Joe Davis and Cal Giddings. It has become a very important concept and approach in the last 5 or 10 years or so, when people started looking at extremely complicated mixtures that had hundreds and thousands of components. And what this theory deals with is how many peaks will you see if the retentions of the sequential peaks are random. That is, they don't come out in lockstep order, equally well resolved, but the peak order, the peak spacing is a random number. And so some peaks are really close together and some are far apart. And then we're going to talk about a subject which is, it seems that we never are able to get away from it. And that's the topic of extra column broadening. I thought for a while that we didn't need to worry about it so much anymore. But in the past few years, the column manufacturers have made the columns so much better, they have so many more plates, that the instruments haven't kept up with the columns. And so the instrument is now a significant part of the broadening process that you see at the end of the peak. The column is certainly a major factor, but is not the overriding dominant factor. So we're back to have to worry about extra column broadening factors. And we're going to talk today, we're going to talk about two of these, and that is what happens when you inject an excessive volume of sample. I'm using the word volume deliberately. I don't mean amount of sample, moles or grams of sample, but the actual volume you inject can be excessive for the column that you're using. And the other factor that's related to this is at the other end of the column, it's your detector. And if you have a detector whose time constant, whose internal mechanism of operation is slow, or its internal volume is large compared to the volume that the peak really occupies as it comes off the column, or the width of the peak in time units as it comes off the column, you're going to get a broadened peak. And you need to be able to quantify that broadening. Before getting started, there's two papers I want you to read. Paper number 9 in your collection is by Sternberg. It is a chapter from an Advances in Chromatography book. This is absolutely the best discussion of extra column broadening that exists in the entire literature. It is a comprehensive treatment of the subject. It's a very long chapter. It's a very detailed chapter. I don't expect you to memorize it. I don't even expect you to understand everything that's in it, but I do expect you to be familiar with the treatment. And it's going to be rough sledding to read this paper, even to browse this paper, until after we go through some of the material today. And hopefully I'll get to extra column broadening today. The other paper is number 10. It's the Davis-Giddings paper, where they introduce the statistical overlap theory. This one, you've got to read it, and read it thoroughly. It's a difficult, challenging paper. Okay, so, general elution problem. This sketch is meant to indicate what happens in the general elution problem. If the conditions that we use in doing the chromatography in GC are isothermal, or in liquid chromatography if the mobile phase composition is maintained constant, and that's what we call isocratic. Constant mobile phase composition. We frequently run into the following situation. At a given temperature or a given composition, we find out that if you arrive at conditions which do a good job of separating the early peaks, that means that they're well resolved. The later peaks tend to be coming out really late and possibly too well separated with a lot of baseline between them. And even if we assume the same number of plates for all the peaks, the later peaks come out and they're stubby and they're broad. And broad peaks are harder to integrate than our narrow peaks because you pick up more noise and they're not as tall as you'd like them to be. So here we've got rather well separated early peaks. I mean, we're virtually getting to baseline there. But in a sense, these later peaks are too well separated. This is better shown in this sequence of chromatograms. Here, let's imagine we're doing a GC run, so our initial run is isothermal. It's relatively cool. So if it's relatively cool, the early peaks are reasonably well retained and they're well separated. However, in this particular mixture, there are 9 compounds. But on this time scale of 30 minutes, we only see 5 compounds. And 6, 7, 8, 9 are coming out next month. So what do? We change the temperature, make the temperature hotter. Everything comes out earlier. We now see 8 peaks, with the 9th peak coming out maybe tomorrow. But look at these early peaks. Peaks 1, 2, 3, and 4 are now squished together. The issue is that it may, in fact, be impossible to find a compromised temperature between too cold and too hot. So what do? We change the temperature during the run. And initially you have a cool temperature which does a good job of handling the early compounds. And then we warm the column up gradually and we make it hot enough so that the last peaks come out in a reasonable period of time. That's what's called temperature programmed gas chromatography. Anybody who would buy a GC without a temperature program device on it is wasting their money. But in the early days of GC, you had no choice. It was strictly isothermal. I think it was Varian that introduced the first temperature program gas chromatograph. Okay, there's the solution to the problem now. It's a temperature programmed GC run, and we have a very nice separation of all 9 of the compounds, including some impurity that the author didn't care to mention as peak. But you see, we're doing a really good job of separating 1, 2, and 3, and peak 9 is coming out in 30 minutes. Now, I don't know if this is the best possible temperature program, but it certainly is a lot better than either too cool or too hot. The same thing can be done in liquid chromatography, but it's not, we usually don't use temperature as a variable for a number of reasons, but Most particularly, temperature does not have as much effect on retention in LC as it does in gas chromatography. Why that's so? So in LC, what we have to do is we change the mobile phase composition. And we start with a relatively weak mobile phase, and then we make it stronger and stronger and stronger as we scan through the separation. In liquid chromatography, that's not called solvent programming, it's called gradient elution. Don't ask me why they decided to change the name. It's the same concept. So we either vary the temperature as a function of time in GC, or we vary the eluent composition as a function of time in LC. I chose simple one-step linear gradients, but a decent GC and a decent LC will give you ways of making very complicated gradients, you know, so that they might do something like that, and then they would go up very rapidly, and then they could have a long hold, and then they might go up even more rapidly. And there's multiple step gradients available both in GC and LC. And in fact, there's nonlinear gradients if you wanted to do nonlinear gradients. And once you got a computer controlling your temperature programmer, or a computer controlling your eluent programmer, you can put in anything you want. In, I think it's the second Snyder paper, he talks about a number of problems that one can run into in chromatography, and he talks about these 6 different types of problems. The general elution problem is one of the problems which he goes over, but there are different problems in each of these cases. I'm not going to go over them. I think it's more than a good idea that you be familiar with different chromatographic issues and suggested ways around them. And I just want to say that temperature programming and gradient elution is not the answer to every single problem that exists in chromatography. Okay, effective plate number. There's 2 different ways to look at this. The first way, and the simplest way, is the following. During the dead volume, when the solute is in the mobile phase, it's not separating from the other types of molecules in the sample. It's just being transported in the mobile phase. And no matter what kind of molecule you're dealing with, they all spend the amount of time and they all spend the same volume in the mobile phase. So is it fair to calculate your plate count using a volume that includes the mobile phase or not? Okay, so some people said, no, it's not fair to include that because it's not contributing to the separation. So what they do is they use a volume or time that's known as the adjusted retention volume, or the adjusted retention volume, by subtracting the dead volume or the dead time from the retention volume or retention time. And then they calculate the plate count. So the effective plate count is defined as the square of the adjusted retention volume or retention time divided by the measured variance of the peak. And the measured variance of the peak, you could estimate if it was a Gaussian peak from the measured half-width of the peak. Or in any other, there's a number of ways you can estimate the variance of the peak. But that's the same number whether you calculate based upon VR or whether you based upon VR prime. But obviously, since you're making the numerators smaller by using the adjusted retention, the effective plate count is reduced. So what these people are really saying is using the straight definition of N, produces an overly optimistic value of the plate count. And they advise against doing that. It turns out that algebraically speaking, the effective plate count will be equal to N, the plate count calculated this way, times K prime over 1 plus K prime squared. You can derive this in a flash on your own. It's a trivial derivation. It's evident that N effective is always less than N because K prime is always less than 1 plus K prime. But this formula really is very interesting because it says something quite important. It says that the effective plate count is essentially 0 if you have no retention. If the K prime is 0, no matter what the plate count is, the effective plate count is zip. Which makes sense. Because we can plug the effective plate number into the resolution equation, and you can see that it subsumes the K prime over 1 plus K prime dependence that's in the general elution equation. So the general elution equation is written like that. Okay, now coming back to this equation, here's the second argument for using the effective plate count. Suppose I got two chromatographic systems that are chemically the same, same stationary phase, same mobile phase, same temperature, but one of them has a higher K prime factor than the other. In other words, one of them has a larger phase ratio than the other. How should I compare the number of plates on those columns? Because there's a big difference in the retention factors. In fact, this is a serious issue. In a little while, we're going to be talking about open tubular capillary gas chromatography. What preceded it experimentally was packed bed gas chromatography. How can you validly compare these two technologies when the retention factors in open tubular capillary GC are a lot smaller than the retention factors in packed beds in general? Or, to put things even in a slightly more modern context, in liquid chromatography, until a few years ago, maybe, let's say, 5 years ago, we used particles that were completely porous. But now we're using particles which are partially porous. They have different plate counts, but the amount of stationary phase that you can put in a partially porous particle is a good deal less than the amount of stationary phase that you can put in a fully porous particle. So how can I compare these legitimately? And you can make a good argument that what you should be using is the effective plate count because it compensates for differences in retention factors. So two different understandings of this effective plate number. Here's a plot of effective plate number divided by the conventional plate number versus retention factor. And this is 10, this is 20. And you can see it just goes up and asymptotically, very slowly approaches unity. And it just follows that relationship between an effective and the plate count. I'm sorry, the peak capacity. Okay. Let's change gears now and get into another somewhat advanced topic, which is the peak capacity. And let's initially consider the situation fitting the conditions during the run. That introduces complications that we don't want to think about at the beginning. The peak capacity is defined as the maximum number of peaks that you can fit between time 1 and time 2, or between volume 1 and volume 2 in the chromatogram. And it's the maximum number of equally well separated peaks. That means that the peaks all have the same resolution. So peak 2 and 1 are as well separated as peaks 3 and 2, 4 and 3, 5 and 4, and all the way out to the last peak that fits in the window. Turns out that the math of adding those up is really not difficult. And we'll get there in a second. But this is what I'm talking about now. I've got 2 times, this time and this time. And I'm going to construct a bunch of peaks, and I'm going to use the same R for all pairs of peaks, and in this case R is going to be 1. And I'm going to assign the same plate count to all of the peaks. And so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 peaks. So the peak capacity of this chromatogram with a resolution of 1 is 16. If you can count, you can do this. Right now, suppose I said I'm not satisfied with a resolution of 1. I want to have a resolution of 1.5. The peaks are going to have to be further apart, aren't they? So I'm not going to be able to fit as many peaks in the same space. And here's a resolution of 1.5. You can see it's a much better resolution because that's just getting down to baseline. And I have a peak capacity now of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 and a half. The lower peak capacity. If I demanded a higher resolution, the peak capacity would go down again. Okay. Now, if I locate my first peak at the dead time of the column or the dead volume of the column, that's peak 1. Now, if I say I want a resolution of such and such, that tells me where my next peak is going to be. If I want a resolution of 1, the next peak maximum is going to have to occur 4 sigma units over. And if I want the third peak to be resolved by R of 1, that has to be over another 4 sigma units, and another, and another, and another. You can do the math, as they say, and the math works out this way, where K prime N is the retention factor of the last peak. N is the plate number, the number of plates you're assuming on all of the columns, and R is the resolution that you're demanding. Well, we almost never use this equation because it's hard to use, and because N is always a much bigger number than R. Even the square root of N is a much bigger number than R. And you can see we have a square root of N plus 2R and the square root of N minus 2R. Well, if you take the limit as R over root N goes to 0, then this function becomes this nice simpler function, except I put RS in there instead of R. RS is the same as R, it's resolution. And so the peak capacity is 1 plus root n over 4R, the natural logarithm of 1 plus the retention factor of the last peak. Now this assumes that the first peak is located at the dead time of the column. So it comes out, and that's peak 1. And that's what generates that 1 there. So even if you have no retention, that is, you say your last peak comes out with no retention, you put in 0, log of 1 is 0, so you still have 1 unit of peak capacity. But generally, the second term is a good deal bigger than the 1. So that's our isocratic isothermal peak capacity. Now, let's look at some numbers. This is K prime N, and this is the number of plates that are on the column, and this is the peak capacity. Now, let's suppose that you chose K prime N to be 5. That's up to you to choose. It's a question of how much time you're willing to put into doing the chromatogram. I mean, it's going to take you 4 times longer to get out to K prime of 20 than it takes you to get to K prime of 5. But if you have 1,000 units of plate count, I mean, that sounds like a big number, right? But it only generates a peak capacity of 15. You can only stick 15 peaks, equally well separated with an R of 1 with that column. If you increase your plate count up to 50,000, a 50-fold increase, at the same K prime N, you get about a 7-fold, 6-fold increase in your number of peaks that you can, your peak capacity. Factor of 50, factor of 6. The square root is not the most favorable relationship in the world. If we go the other way, and let's look at, keep the plate count constant, but increase the K prime, we change from 5 to 20. It's going to take us 4 times longer to do the separation. Don't even double it. Not happy camper. Spend 4 times as much time doing the darn separation, and you just barely, you don't even double your peak capacity. It's really not a wonderful world. Unfortunately, this is the best possible situation because you've assumed that the peaks are willing to just line themselves up and come out lockstep and assume that they're all perfectly well, 1 unit of resolution, 1 unit, 1 unit, 1 unit. Mother Nature doesn't give you samples that look like that. Giddings and Davis said it's much more likely that the peaks are randomly spaced relative to one another. And they then proceeded to work out the mathematics of this situation, assuming a random relationship between the retention times. And their analysis of the situation is called statistical overlap theory, and nobody ever says that, it's SOT. And we'll knock off here. But this is the initial situation we're talking about where everybody's lockstep. And we're going to build on this theme, and we're going to let the peak positions be non-uniform. And we're going to see how many peaks we get. And it's going to be a lot less than the peak capacity, a lot less. Okay.